In the previous video, we gave a mathematical definition of gradient descent. Let's delve deeper and in this video get better intuition about what the algorithm is doing and why the steps of the gradient descent algorithm might make sense. Here's the gradient descent algorithm that we saw last time. And just to remind you, this parameter or this term alpha is called the learning rate, and it controls how big a step we take when updating my parameter theta j. And this second term here is the derivative term. And what I want to do in this video is give you better intuition about what each of these two terms is doing and why, when put together, this entire update makes sense. In order to convey these intuitions, what I want to do is use a slightly simpler example where we want to minimize a function of just one parameter. So we have, say we have a cost function j of just one parameter, theta 1, like we did a few videos back, where theta 1 is a real number. Okay, so just again, so we can have 1D plots, which are a little bit simpler to look at. And let's try to understand what gradient descent will do on this function. So let's say here's my function j of theta 1. And so that's my, and where theta 1 is a real number. Right? Now, let's say I've initialized gradient descent with theta 1 at this location. So imagine that we start off at that point on my function. What gradient descent will do is it will update theta 1, gets updated as theta 1 minus alpha times dd theta 1 j of theta 1, right? And as an aside, this derivative term, right? If you're wondering why I changed the notation from these partial derivative symbols, if you don't know what the difference is between these partial derivative symbols and the dd theta, don't worry about it. Technically, in mathematics, we call this a partial derivative, we call this a derivative, depending on the number of parameters in the function j. But that's a mathematical technicality. So, for the purpose of this lecture, think of these partial symbols and dd theta 1 as exactly the same thing, and don't worry about whether there are any differences. I'm going to try to use the mathematically precise notation, but for our purposes, these two notations are really the same thing. But so let's see what this equation will do. So we're going to compute this derivative. I'm not sure if you've seen derivatives in calculus before, but what the derivative at this point does is basically saying, let's take the tangent to that point, like that straight line, that red line, is just touching this function. And let's look at the slope of this red line. That's what the derivative is. It says, what's the slope of a line that is just tangent to the function? Okay, and the slope of a line, of course, is just, right, this height divided by this horizontal thing. Now, this line has a positive slope, so it has a positive derivative. And so my update to theta is going to be theta 1 gets updated as theta 1 minus alpha times some positive number. Okay, and alpha, the learning rate, is always a positive number. And so I'm going to take theta 1 gets updated as theta 1 minus something. So I'm going to end up moving theta 1 to the left. I'm going to decrease theta 1. And we can see this is the right thing to do because I actually want to head in this direction, to get me closer to the minimum over there. So gradient descent so far seems to be doing the right thing. Let's look at another example. So let's take my same function j. Let's try to draw the same function, j of theta 1. And now, let's say I had instead initialized my parameter over there on the left. So theta 1 is here. I'm going to at that point on the surface. Now, my derivative term, dd theta 1, j of theta 1, when evaluated at this point, I'm going to look at, right, the slope of that line. So this derivative term is the slope of this line. But this line is slanting down, so this line has negative slope. Right? Or alternatively, I say that this function has negative derivative, just means negative slope at that point. So this is less than or equal to 0. So when I update theta, I'm going to have theta gets updated as theta minus alpha times a negative number. And so I have theta 1 minus a negative number, which means I'm actually going to increase theta, right? Because this is minus of a negative number. It means I'm adding something to theta. And what that means is that I'm going to end up increasing theta. And so I'm going to start here and increase theta, which again seems like the thing I wanted to do to try to get me closer to the minimum. So this hopefully explains the intuition behind what the derivative term is doing. Let's next take a look at the learning rate term alpha and try to figure out what that's doing. So here's my gradient descent update rule, right? It's this equation. And let's look at what could happen if alpha is either too small or if alpha is too large. So in this first example, what happens if alpha is too small? So here's my function j of theta. Let's say I start here. If alpha is too small, then what I'm going to do is going to multiply my update by some small number. So I end up taking, it's like a baby step like that. Okay? So that's one step in descent. Then from this new point, I'm going to take another step, but if alpha is too small, I'm going to take another little baby step. And so if, if my learning rate is too small, I'm going to end up, taking these tiny, tiny baby steps to try to get to the minimum. And I'm going to need a lot of steps to get to the minimum. And so if alpha is too small, gradient descent can be slow because it's going to take these tiny, tiny baby steps, and so it's going to need a lot of steps before it gets anywhere close to the global minimum. Now, how about if alpha is too large? So here's my function j of theta. Turns out if alpha is too large, then gradient descent can overshoot the minimum and may even fail to converge or even diverge. So here's what I mean. Let's say I start off theta there. It's actually pretty close to minimum. So the derivative points to the right, but if alpha is too big, I'm going to take a huge step. Maybe I'll take a huge step like that. Right? So I end up taking a huge step. And now my cost function has actually gotten worse because I start off with this value, but now my value has actually gotten worse. Now my derivative points to the left. It says I should decrease theta. But if my learning rate is too big, I may take a huge step going from here all the way out there. So I end up going out there, right? And if my learning rate is too big, I can take another huge step on the next iteration and kind of overshoot and so on until you notice I'm actually getting further and further away from the minimum. And so if alpha is too large, it can fail to converge or even diverge. Now, I have another question for you. So this is a tricky one, and when I was first learning this stuff, it actually took me a long time to figure this out. What if your parameter theta 1 is already at the local minimum? What do you think one step of gradient descent will do? So let's suppose you initialize theta 1 at the local minimum. So suppose this is your initial value of theta 1 over here, and is already at a local optimum, or the local minimum. It turns out the local optimum, your derivative will be equal to 0. So let's look at that slope, right? It's that tangent point. So the slope of this line will be equal to 0, and thus this derivative term is equal to 0. And so in your gradient descent update, you have theta 1 gets updated as theta 1 minus alpha times 0. And so what this means is that if you're already at the local optimum, it leaves theta 1 unchanged because gets updates theta 1 equals theta 1. So if your parameter is already at the local minimum, one step of gradient descent does absolutely nothing. It doesn't change the parameter, which is what you want because it keeps your solution at the local optimum. This also explains why gradient descent can converge to local minimum even with the learning rate alpha fixed. Here's what I mean by that. Let's look at an example. So here's a cost function j of theta that maybe I want to minimize. And let's say I initialize my algorithm, my gradient descent algorithm, out there at that magenta point. If I take one step of gradient descent, maybe it'll take me to that point because my derivative is pretty steep out there, right? Now I'm at this green point, and if I take another step of gradient descent, you notice that my derivative, meaning the slope, is less steep at the green point than compared to at the magenta point out there, right? Because as I approach the minimum, my derivative gets closer and closer to 0 as I approach the minimum. So after one step of gradient descent, my new derivative is a little bit smaller, So when I take another step of gradient descent, I will naturally take a somewhat smaller step from this green point than I did from the magenta point. Now I'm at a new point, the red point, and then now even closer to the global minimum. So the derivative here will be even smaller than it was at the green point. So when I take another step of gradient descent, now my derivative term is even smaller, and so the magnitude of the update to theta 1 is even smaller. So take a small step like so. And as gradient descent runs, you will automatically take smaller and smaller steps until eventually you're taking very small steps, and you finally converge to the local minimum. So just to recap, in gradient descent, as we approach a local minimum, gradient descent will automatically take smaller steps. And that's because as we approach the local minimum, by definition, the local minimum is when this derivative is equal to 0. So as we approach the local minimum, this derivative term will automatically get smaller, and so gradient descent will automatically take smaller steps. So this is what gradient descent looks like, and there's so actually no need to decrease alpha over time. So that's the gradient descent algorithm, and you can use it to try to minimize any cost function j, not the cost function j that we defined for linear regression. In the next video, we're going to take the function j and set that back to be exactly linear regression's cost function, the squared cost function that we came up with earlier, and taking gradient descent and the squared cost function and putting them together, that will give us our first learning algorithm. That will give us our linear regression algorithm. In previous videos, we talked about the gradient descent algorithm, and we talked about the linear regression model and the squared error cost function. In this video, we're going to put together a gradient descent with our cost function, and that will give us an algorithm for linear regression, for fitting a straight line to our data. So this was what we worked out in the previous videos. There's our gradient descent algorithm, which should be familiar. And here's the linear regression model with our linear hypothesis and our squared error cost function. What we're going to do is apply gradient descent to minimize our squared error cost function. Now, in order to apply gradient descent, in order to write this piece of code, the key term we need is this derivative term over here. So we need to figure out what is this partial derivative term, and plugging in the definition of the cost function j, this turns out to be this, sum from I equals 1 through m of this squared error cost function term. And all I did here was I just plugged in the definition of the cost function there. And simplifying a little bit more, this turns out to be equal to this, sum from I equals 1 through m of theta 0 plus theta 1 xi minus yi squared. And all I did there was I took the definition for my hypothesis and plugged it in there. And turns out we need to figure out what is this partial derivative for two cases, for j equals 0 and for j equals 1. So we want to figure out what is this partial derivative for both the theta 0 case and the theta 1 case. And I'm just going to write out the answers. It turns out this first term is simplifies to 1 over m sum from over my training set of just that, xi minus yi. And for this term, partial derivative with respect to theta 1, it turns out I get this term, minus yi times xi. Okay? And computing these partial derivatives, so that going from this equation, going from this equation to either of the equations down there, computing those partial derivative terms requires some multivariate calculus. If you know calculus, feel free to work through the derivations yourself and check that if you take the derivatives, you actually get the answers that I got. But if you are less familiar with calculus, don't worry about it, and it's fine to just take these equations that were worked out, and you won't need to know calculus or anything like that in order to do the homework or to implement gradient descent and get that to work. But so armed with these definitions, or armed with what we worked out to be the derivatives, which is really just the slope of the cost function j, we can now plug them back into our gradient descent algorithm. So here's gradient descent for linear regression. We're just going to repeat until convergence. Theta 0 and theta 1 get updated as, this thing minus alpha times the derivative term. So this term here. So here's our linear regression algorithm. This first term here, that term is, of course, just the partial derivative with respect to theta 0 that we worked out on the previous slide. And this second term here, that term is just the partial derivative with respect to theta 1 that we worked out on the previous slide. And just as a quick reminder, you must, when implementing gradient descent, there's actually this detail that you should be implementing it so the update theta 0 and theta 1 simultaneously. So let's see how gradient descent works. One of the issues we saw with gradient descent is that it can be susceptible to local optima. So when I first explained gradient descent, I showed you this picture of it, going downhill on the surface, and we saw how, depending on where you initialize it, you can end up at different local optima. You end up, here or here. But it turns out that the cost function for linear regression is always going to be a bow-shaped function like this. The technical term for this is that this is called a convex function. And I'm not going to give the formal definition for what is a convex function, C-O-N-V-E-X, but informally, a convex function means a bow-shaped function, kind of like a bow-shaped. And so this function doesn't have any local optima except for the one global optimum. And does gradient descent on this type of cost function, which you get whenever you're using linear regression, it will always converge to the global optimum because there are no other local optima other than the global optimum. So now let's see this algorithm in action. As usual, here are plots of the hypothesis function and of my cost function j. And so let's say I've initialized my parameters at this value. Let's say usually you initialize your parameters at 0, 0, theta 0, and theta 1 equals 0. But for illustration, in this particular implementation of gradient descent, I've initialized theta 0 at about 900 and theta 1 at about minus 0.1. Okay, and so this corresponds to h of x equals minus 900 minus 0.1x is this line. And so we're out here on the cost function. Now, if we take one step of gradient descent, we end up going from this point out here, a little bit to the down and left, to that second point over there. And you notice that my line changed a little bit. And as I take another step of gradient descent, my line on the left will change, right? And I've also moved to a new point on my cost function. And as I take further steps of gradient descent, I'm going down in cost, right? So my parameters is sort of following this trajectory. And if you look on the left, this corresponds to hypotheses that, seem to be getting to be better and better fits to the data until eventually I've now wound up at the global minimum, and this global minimum corresponds to this hypothesis, which gives me a good fit to the data. And so that's gradient descent, and we've just run it and gotten a good fit to my data set of housing prices, and you can now use it to predict, if your friend has a house that costs of size 1250 square feet, you can now read off the value and tell them that, I don't know, maybe they can get $250,000 for their house. Finally, just to give this another name, it turns out that the algorithm that we just went over is sometimes called batch gradient descent. And it turns out in machine learning, I don't know, I feel like us machine learning people, we're not always great at giving names to our algorithms. But the term batch gradient descent means that refers to the fact that in every step of gradient descent, we're looking at all of the training examples. So in gradient descent, when computing derivatives, we're computing these sums, right? This sum of. So in every step of gradient descent, we end up computing something like this that sums over all m training examples. And so the term batch gradient descent refers to the fact that we're looking at the entire batch of training examples. And again, this is really maybe not a great name, but this is what machine learning people call it. And it turns out that there are sometimes other versions of gradient descent that are not batch versions, but that instead do not look at the entire training set, but look at small subsets of the training set at a time. And we'll talk about those versions later in this course as well. But for now, using the algorithm you just learned about, or using batch gradient descent, you now know how to implement gradient descent for linear regression. So that's linear regression with gradient descent. If you've seen advanced linear algebra before, so some of you may have taken a class in advanced linear algebra, you might know that there exists a solution for numerically solving for the minimum of the cost function j without needing to use an iterative algorithm like gradient descent. Later in this course, we'll talk about that method as well, that just solves for the minimum of the cost function j without needing just multiple steps of gradient descent. That other method is called the normal equations method. But in case you've heard of that method, it turns out that gradient descent will scale better to larger data sets than that normal equation method. And now that we know about gradient descent, we'll be able to use it in lots of different contexts, and we'll use it in lots of different machine learning problems as well. So, congrats on learning about your first machine learning algorithm. We'll later have exercises in which we'll ask you to implement gradient descent and hopefully see these algorithms work for yourselves. But before that, I first want to tell you in the next set of videos, I first want to tell you about a generalization of the gradient descent algorithm that will make it much more powerful. And I guess I'll tell you about that in the next video. Let's get started with our linear algebra review. In this video, I want to tell you what are matrices and what are vectors. A matrix is a rectangular array of numbers written between square brackets. So for example, here is a matrix. I'm going to write a left square bracket and then write in a bunch of numbers. And these could be features for a machine learning problem, or it could be data from somewhere else. But for example, the specific values don't matter. And then I'm going to close it with another right bracket on the right. And so that's one matrix. And here's another example of a matrix. I'm just going to write 1, 2, 3, 4, 5, 6. So a matrix is just another way for saying is a 2D or a two-dimensional array. And the other piece of terminology we need is that the dimension of a matrix is going to be written as the number of rows times the number of columns in the matrix. So concretely, this example on the left, this has 1, 2, 3, 4 rows, and it has 2 columns. And so this example on the left, I'm going to say this is a 4 by 2 matrix, okay? Because it's number of rows by number of columns, so 4 rows, 2 columns. This one on the right, this matrix has 2 rows. So that's the first row, that's the second row, and it has 3 columns, right? That's the first column, that's the second column, that's the third column. So this second matrix, we say it is a 2 by 3 matrix, or we say that the dimension of this matrix is 2 by 3. And sometimes you also see this written out as, in the case of the left, you see this written out as R4 by 2. Or concretely, what people will sometimes say is that this matrix is an element of the set R4 by 2. So this thing here, this just means a set of all matrices that are of dimension 4 by 2. And this thing on the right, sometimes this is written out as a matrix that's an R2 by 3. So if you ever see, 2 by 3. So if you ever see something like this, R4 by 2 or R2 by 3, people are just referring to matrices of a specific dimension. Next, let's talk about how to refer to specific elements of the matrix. And by matrix elements, or elements of the matrix, I just mean the entries or the numbers inside the matrix. So in the standard notation, if A is this matrix here, then A subscript ij is going to refer to the I comma j entry, meaning the entry in the matrix is in the ith row and the jth column. So for example, A11 is going to refer to the entry in the first row and the first column. So that's the first row and the first column. And so, A11 is going to be equal to 1402. Another example, A12 is going to refer to the entry in the first row and the second column. And so A12 is going to be equal to 191. Just a couple more quick examples. Let's see. Let's say A32 is going to refer to the entry in the third row and the second column, right? Because that's 32, so that's equal to 1437. And finally, A41 is going to refer to, this one, right? Fourth row, first column is equal to 147. And if, hopefully you won't, but if you were to say, what is A43? Well, that refers to the fourth row and the third column, but, this matrix has no third column, so this is undefined, or you can think of this as an error. So there's no such element as a A43, so, shouldn't be referring to A43. So the matrix gives you a way of letting you quickly organize, index, and access lots of data. And in case I seem to be tossing up a lot of concepts, a lot of new notation very rapidly, you don't need to memorize all this, but on the course website, where we have posted the lecture notes, we also have all of these definitions written down. So you can always refer back, either to these slides posted on the course website or to the lecture notes if you forget, A41 is that, which row, which column is that. Don't worry about memorizing everything now. You can always refer back to the written materials on the course website. Use that as a reference. So that's what a matrix is. Next, let's talk about what is a vector. A vector turns out to be a special case of a matrix. A vector is a matrix that has only one column. So if you have an n by 1 matrix, then that's remember, right? N is the number of rows, and 1 here is the number of columns. So a matrix with just one column is what we call a vector. So here's an example of a vector, right? With, I guess I have n equals 4 elements here. So we also call this thing, another term for this is that this is a 4-dimensional vector. It just means that this is a vector with 4 elements, with 4 numbers in it. And just as earlier for matrices, you saw this notation like R3×2 to refer to 3×2 matrices, right? For this vector, we're going to refer to this as a vector in the set R4. So this R4, again, just means a set of all 4-dimensional vectors. Next, let's talk about how to refer to elements of the vector. We're going to use the notation yi to refer to the ith element of the vector y. So if y is this vector, y subscript I is the ith element. So y1 is the first element, is equal to 460. Y2 is equal to the second element, right? 232. That's the first, that's the second. Y3 is equal to 315, and so on. And only y1 through y4 are defined because this is a 4-dimensional vector. Also, it turns out that there are actually 2 conventions for how to index into a vector. And here they are. Sometimes people will use 1 index and sometimes 0 index vectors. So this example on the left is a 1 index vector where the elements we write as y1, y2, y3, y4. And this example on the right is an example of a 0 index vector where we start the indexing of the elements from 0. So the elements go from y0 up to y3. And this is a little bit like the arrays of some programming languages, right, where the arrays can either be indexed starting from 1, so the first element of an array is sometimes say y1, this kind of C++ notation, I guess, and sometimes is 0 index, depending on what programming language you use. So it turns out that in most of math, the 1 index version is more common, But for a lot of machine learning applications, zero index vectors gives us a more convenient notation. So what you should usually do is, unless otherwise specified, you should assume that we're using one index vectors. In fact, throughout the rest of these videos on linear algebra review, I will be using one index vectors. But just be aware that when we talk about machine learning applications, sometimes I'll explicitly say when we need to use zero index vectors as well. Finally, by convention, usually when writing matrices and vectors, most people will use uppercase to refer to matrices. So when we use capital letters like A, B, C, X to refer to matrices, and usually we'll use lowercase like A, B, X, Y to refer to either numbers, just real numbers or scalars, or to vectors. But this isn't always true, but this is the more common notation where we use lowercase y to refer to vector, and we usually use uppercase to refer to a matrix. So you now know what are matrices and vectors. Next, we'll talk about some of the things you can do with them. In this video, we'll talk about matrix addition and subtraction, as well as how to multiply a matrix by a number, also called scalar multiplication. Let's start with an example. Given two matrices like these, let's say I want to add them together. How do I do that? And so what does addition of matrices means? It turns out that if you want to add two matrices, what you do is you just add up the elements of these matrices one at a time. So my result of adding two matrices is going to be itself another matrix. And the first element I get just by taking 1 and 4 and multiplying them and adding them together. So I get 5. The second element I get by taking 2 and 2 and adding them. So I get 4. 3 plus 0 is 3, and so on. I'm going to stop changing colors, I guess. And on the right is 0.5, 10, and 2. And it turns out you can add only two matrices that are of the same dimension. So this example is a 3 by 2 matrix because this has 3 rows and 2 columns, so it's 3 by 2. This is also a 3 by 2 matrix, and the result of adding these two matrices is a 3 by 2 matrix again. So you can only add matrices of the same dimension, and the result will be another matrix that's of the same dimension as the ones you just added. Whereas in contrast, if we were to take these two matrices, so this one is a 3 by 2 matrix, so again, 3 rows, 2 columns. This here is a 2 by 2 matrix. And because these two matrices are not of the same dimension, this is an error. So you cannot add these two matrices, and their sum is not well defined. So that's matrix addition. Next, let's talk about multiplying matrices by a scalar number. And a scalar is just maybe an overly fancy term for a number or a real number. Right? The scalar just means real number. So let's take the number 3 and multiply it by this matrix. If you do that, the result is pretty much what you'd expect. You just take your elements of the matrix and multiply them by 3 one at a time. So 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. And let's see, I'm going to stop changing colors again. 0 times 3 is 0. 3 times 5 is 15. And 3 times 1 is 3. And so this matrix is the result of multiplying that matrix on the left by 3. And you notice, again, this is a 3 by 2 matrix, and the result is a matrix of the same dimension. This is a 3 by 2. Both of these are 3 by 2 dimensional matrices. And by the way, you can write multiplication either way. So I had 3 times this matrix. I could also have written this matrix 1, 0, 2, 5, 3, 1, right? I just copied this matrix over to the right. I can also take this matrix and multiply this by 3. So whether it's 3 times the matrix or the matrix times 3 is the same thing, and this thing here in the middle is the result. You can also take a matrix and divide it by a number. So turns out taking this matrix and dividing it by 4, this is actually the same as taking the number 1/4 and multiplying it by this matrix, 4063. And so, you can figure the answer. The result of this product is, 1/4 times 4 is 1, 1/4 times 0 is 0, 1/4 times 6 is, 3/2. That 6/4 is 3/2, and 1/4 times 3 is 3/4. And so that's the result of computing this matrix divided by 4. That gives you the result. Finally, for a slightly more complicated example, you can also take these operations and combine them together. So in this calculation, I have 3 times a vector plus a vector minus another vector divided by 3. So just make sure we know what these are, right? This multiplication, this is an example of scalar multiplication, because I'm taking 3 and multiplying it. And this is, another scalar multiplication, or one of our scalar division, I guess, is really just means 1/3 times this. And so if we evaluate these two operations first, then what we get is this thing is equal to, let's see, so 3 times that vector is 3, 12, 6, plus my vector in the middle, which is a 0, 0, 5, minus 1, 0, 2/3, right? And again, just to make sure we understand what's going on here, this plus symbol, that is matrix addition, right? Or really, since these are vectors, remember vectors are special cases of matrices, right? We can also call this vector addition. And this minus sign here, this is again, matrix subtraction. But because this is a n by 1, really a 3 by 1 matrix, that this is actually a vector. So this is also vector. Just call this matrix a vector subtraction as well. Okay? And finally, to wrap this up, this therefore gives me a vector whose first element is going to be 3 plus 0 minus 1. So that's 3 minus 1, which is 2. The second element is 12 plus 0 minus 0, which is 12. And the third element of this is 6 plus 5 minus 2/3, which is 11 minus 2/3, so that's 10 and 1/3. And I'm going to close my square bracket. And so this gives me a 3 by 1 matrix, which is also just called a 3-dimensional vector, right? Which is the outcome of this calculation over here. So that's how you add and subtract matrices and vectors and multiply them by scalars, or by real numbers. So far, I've only talked about how to multiply matrices and vectors by scalars, by real numbers. In the next video, we'll talk about a much more interesting step of taking two matrices and multiplying two matrices together.